So now that we talked about how to set up the idea of a hypothesis test, we're now going to look at the mechanics of doing a hypothesis test. The first type of situation we're going to deal with is doing a hypothesis test for a population mean. So the objective will be to test a hypothesis about a mean and understand the difference between statistical significance and practical significance. For a test of a hypothesis about a mean, we're going to use either the t-distribution or the z-distribution, depending on how much information that we know. If we happen to know the population standard deviation, we can use sigma in our formula, and therefore we can use the z-distribution. Since that will very rarely occur, and we will almost always be using the sample standard deviation s to estimate sigma, we will do all of these tests for the population mean using the t-distribution in its place. The formula for the t statistic is x bar minus mu over s over the square root of n. It does follow a student's t-distribution with n minus 1 degrees of freedom. So in everything we do in this section, we're going to deal with the t-distribution with n minus 1 degrees of freedom, where n is the sample size. The t-distribution is different for different degrees of freedom. We saw that in our previous lecture, that the larger the degrees of freedom, the closer this thing is to the normal. The smaller the number of degrees of freedom, the more weight there is in the tail. It is still centered about 0 and symmetric. It is still a distribution, so the area under the curve is 1. The area to the left of 0 is a half, and the area to the right of 0 is a half because of that symmetry. And as t increases without bound, the graph approaches 0 but never equals it. Again, the further we get away from 0, the smaller the probability it is, but there will still be some positive probability. And the reason that we have more room in the tails is because we're using s to estimate sigma. As the sample size increases, that t-distribution will get closer to the normal curve. So those are all things that we talked about previously. In order for us to test a hypothesis about the population mean, we're going to use that t-distribution and its properties to help us come up with the likelihood of observing a sample, assuming that the null hypothesis is true. Some things we have to make sure happen when we're testing a hypothesis is that the sample is obtained by a simple random process. Okay. So we want simple random sampling or some sort of random sampling. The sample has no outliers, and the population from which a sample is drawn is normally distributed, or the sample size is large. The sample values are independent of each other. Okay. So we want things to be independent, and we want to be leery of any sets that have outliers. We're going to first have to determine the null and alternative hypothesis. And again, it could be one of three things: not equal, less than, or greater than for the alternative. The null hypothesis, notice in all three cases, is an equality statement. We have to select a level of significance. Typically, alpha will be 0.05 or 5%. That's the level at which we're willing to accept a type 1 error. We're then going to compute the test statistic. So based off of the null hypothesis that we have, the hypothesized mean, we're going to see how far away from that hypothesized mean our sample mean is. So we're going to take the sample mean minus a hypothesized mean and divide by s over the square root of n to get an estimate of the number of steps we are away from the hypothesized mean. We're then going to compare that to a critical value. If we exceed that critical value, then we will reject the null hypothesis. This is what's called the classical approach. If it's a two-tailed test, we could either be too far out to the right or too far out to the left. If the value we observe is too far out to the right or too far out to the left, we're going to reject the null hypothesis. In a one-tailed approach, we'll have a direction. If we go too far out in that particular direction, we will reject the null hypothesis. Too far to the right, that's where our t-table will come in. We'll find a critical value based off of the level of alpha that we set and the number of degrees of freedom. And if we exceed that critical value, then we will reject the null hypothesis. For the p-value approach, we'll still calculate the t-statistic, but now instead of comparing to some critical value, we'll estimate how often this value occurs by looking at something in our t-table and trying to determine what probability it is associated with. So we will use the t-table to approximate that p-value. So in other words, we will look up a value, our t-value in the table, and try to come up with an approximate area. If we are in a two-sided test, we're only going to have one test statistic. That's going to either be to the right or to the left. But with a two-sided approach, since it could go either way, we'll have to take that value and double it to get our overall p-value. For a one-sided approach, it's just a matter of looking up what the percent of the time that value could occur. So whatever percent we come up with on our table will be our p-value. If we're using a t-table, we will have to probably settle for a range of estimates for the p-value because we don't have enough specific information. If you're using a statistical package like StatCrunch, it will go ahead and calculate the exact p-value for you because it has more information stored than what we have on that one table. If you use a spreadsheet or a calculator or something like Minitab or StatCrunch, it will give you a p-value when running. Way to think about that is this type 1 error is how often we would consider an event to be rare. So in other words, something that happens less than alpha percent of the time would be considered too rare to be considered a normal situation. And so it would lead us to reject the null hypothesis. So if the p-value is more rare than alpha, then we will reject the null hypothesis. If what we observe happens less than the threshold we set for alpha, then we'll reject the null hypothesis. We'll then, in either the classical approach or the p-value approach, state the conclusion. We'll either reject the null hypothesis in favor of the alternative, or we'll fail to reject the null hypothesis. This procedure is what we call robust, meaning that minor departures from normality will not adversely affect the results of the test. However, for small samples, if the data have outliers, the procedure should not be used. So in other words, if I take samples of size 4 or 5, and I have some points that are somewhat grouped together, and then one that's way out to the right or way out to the left that will dramatically, then this is probably not going to be a good test for me to run. So let's take an example. Assume the resting metabolic rate of healthy males is in complete silence is 5,710 kilojoules per day. Researchers measured that resting metabolic rate of 45 healthy males who were listening to calm classical music and found that their RMR was 5,708.07 kilojoules per day with a standard deviation of 992.05. At the 0.05 level of significance, is there evidence to conclude that the RMR of males listening to calm classical music is different than 5,710 kilojoules? Hypothesized mean of 5,710 and see how many standard deviations that is away. Where again, remember, standard deviation is going to be the standard deviation of the sample divided by the square root of n. So we're going to calculate a two-tailed test because it just says that it's different, not that it's less than or greater than. We're making a null hypothesis that the mean is 5,710 kilojoules per day. The alternative is that it's just not 5,710. We know that X bar is 5708.07 and S is 992.05. Statistic is minus 0.013. So that means we were 0.013 steps left of the mean. That's not very far from the mean. So just looking at that, I can tell that we're not going to have a significant difference, but let's look at it. Since this is a two-tailed test, we're going to determine the critical values at the alpha's 0.05 level, and we're going to do that with a 44 degrees of freedom. Because it's two-tailed, we know we have to split that 5% into two tails, so that means we're going to be looking at 0.025. So we're going to go to the 0.025 column in the table, and we'll go to the 44 row. Now, the table I showed you doesn't have 44. It only has 40. If I were using this table, I would use the thing that was closest to 44 but was smaller. And if I look at the 0.025 column, that's this one, scrolling down, that would give me a value of 2.021. So I would have a critical value of 2.021. Notice that's the value that we have here. Why is it negative? Well, if I'm moving out to the left, that negative indicates the direction. So I could either go left 2.021 steps, or I could go right 2.021 steps. If I either go more than 2.021 steps to the left or 2.021 steps to the right, I know there's going to be a problem. This is not 2.021 steps away or more. So we are not further out than our critical values, therefore we fail to reject that null hypothesis. Let's go back and look at the p-value approach. We know that we have 0.013 is our t-value. We're going to look at the absolute value because this thing is symmetric. And if I want being more than 0.013, I would have, well, let's see, on my 40 row, looking for a t-value of 0.013, well, the smallest t-value I have is 0.255, and that happens greater than 40% of the time. So I know that one tail is greater than 40%, so two tails would be more than 80%. So I know that my p-value is more than 80%. In this case, the table that they give you in the textbook stops and would you be stuck with more than 25%. In other words, being off by 0.013 standard deviations is not very rare at all. That would be considered a very normal result, and therefore we have no evidence to suggest that the mean or that the null hypothesis is false. Okay. Let's take a different example, and let's hope that our numbers come out a little bit further so we get some better numbers to work with. Say we start with 18 weights of state quarters. And according to the Mint, the quarters are supposed to weigh 5.67 grams. So again, what we have in this situation is a weight that the quarters are supposed to be. We're now going to check the validity of that assumption. And we want to know if the weight is different than 5.67. So we take the average of those 18 to come up with a sample average. We're looking at whether or not the weight is different, so it's two-tailed. So we're going to go through the process. First of all, we try to see if the assumption of normality is reasonable. And this is a plot that will allow us to do that. We may spend some time in a lab talking about how we could check that normality assumption. But for the homework problems and the exam problems, you should assume that we satisfy that normal assumption and concentrate on the calculations. So our null hypothesis is that the mean weight is 5.67 grams. The alternative is that it's not 5.67 grams. We chose a level of significance of 5%, which means we're going to have 2.5% in each tail. The average of the sample of 18 coins that we got was 5.7022 grams, with a standard deviation of 0.0497. If we plug that into our test statistic of x bar minus the hypothesized mean over s over the square root of n, we come up with 2.75 standard deviations. So our average weight is 2.75 standard deviations above the mean. 2.75 standard deviations above the mean seems like it might be something that is significant. So let's go in and look at our table. Remember, we had 18 observations, so that gives us 17 degrees of freedom. We had a two-tailed test with a significance level of 5%. Since it's two-tailed, that means this 5% is split up, and we would have 2.5% in each tail. So we're going to go to our table, and we're going to look up in the 0.025 column on the 17 row. So we're going to go to the 0.025 column. In the 17 row, so there's 17 and 0.025, and that gives me a t-value of 2.11. So this is the number of steps that I need to be away before I think there's an issue. And it could go right or left because I'm in a two-tailed test. So I know that if I go more than 2.11 standard deviations to the right, there's a problem. Or if I go more than 2.11 standard deviations to the left, there's going to be a problem. Since my test statistic is more than 2.11 standard deviations away from the mean, we reject the null hypothesis. What does that mean? That means that we conclude that the average weight of those coins is not 5.67 grams. We've rejected the null hypothesis, means the null hypothesis we assumed was true. We now have enough evidence to say it's actually false. For the p-value approach, we would go to the see where we came up with 2.75 in that table. So I'm going to go to the 17 row. I'm going to try to find where 2.75 would lie, and notice that's in between 2.567 and 2.898. So I know one tail has a probability of between 0.005 and 0.01. So half of my total probability is between 0.005 and 0.01. So the total p-value would be double this, is somewhere between 0.01 and 0.02. So the one p-value going greater than 2.75 was somewhere between 0.005 and 0.01. Doubling that gives me a value between 0.01 and 0.002. Since 0.02 is less than 0.05, we know we would reject the null hypothesis. So there is sufficient evidence to conclude that the mean weight of state quarters differs from the 5.67 grams. We will do some additional examples outside of this lecture with one-tailed test. So let's distinguish between the idea of statistical and practical significance. When a large sample size is used in a hypothesis test, the results could be statistically significant, even though the difference between the sample statistic and the mean may have no practical significance. Practical significance refers to the idea that while small differences between the statistic and parameter stated in the null hypothesis are statistically significant, the difference may not be large enough to cause concern or be considered important. For example, in 2003, the average age of a mother at the time of her first childbirth was 25.2 years. To determine if the average age has increased, a random sample of 1,200 mothers is taken and is found to have a sample mean average of 25.5 with a standard deviation of 4.8 years. Determine whether the mean age has increased using a significance level of alpha 0.05. Because of the very large sample that we've taken, we are almost guaranteed that any difference between our sample mean and a hypothesized mean will be statistically significant. But in reality, you're looking at 0.3 of a year, so maybe 3 to 4 months difference in the average age. That's probably not going to cause us to go out and make any changes in our recommendations for health considerations or anything where we're advising the first-time mother on what might be considered normal for their pregnancy based off of their age. So practically speaking, there's not really a difference between 25.5 and 25.2 in how we'll handle the situation, but because of the large sample size that we took, there will be a statistical significance. And if we go through the process, we can see that we get a t-value of 2.17 with 1,199 degrees of freedom. A t-value of 2.17 gives us a p-value of somewhere between 0.01 and 0.02. So it is very significant statistically. It's much smaller than the 5% level that we set, but practically speaking, it's not going to change the way we do things. Another example would be an IQ test where the average is 100, and we take a large sample from 2,000 or 3,000 students, and we find an average of 101. Because of a large sample size, there is a statistical significant difference, but practically speaking, there's not going to be any difference between how we're going to treat somebody with 100 IQ and 101 IQ. If we're basing anything on a standardized test, we're not going to go out and change all of our formulas and all of our